it's Hiii, Math Angel. Welcome back. This is Decaf-Math ASMR. I hope that you're doing well. It's been a little while since I last uploaded, so my apologies to those of you who enjoy watching my newest videos regularly. But I'm very glad to be here right now, and I hope that you feel welcome to just relax for a bit with me. Today I'm going to focus on gently soft speaking like this and going in and out of a whisper, because I've gotten some feedback that people really enjoy that here, so I'm here for you. So that's what I'm going to do, and I'm going to chat about a concept from Linear Algebra, just some random topic, and this is on null spaces and the nullity of said null space when I'm given a matrix. So I just want to focus more on the big picture idea today. We're going to review some concepts here, but since math often builds on itself, I don't want there to be a lot of pressure, so I'm going to go ahead and overlay some of the more tedious calculations, and then this way we can focus on the big picture and you can follow along with what you feel like and just kind of feel free to zone out the rest. As always, everyone is welcome here, so it doesn't matter if you know this or you don't. It doesn't matter if you like math or not. There's never any pressure, and I jump around a lot of different topics, so unless you just happen to be reviewing this particular concept, you should pay attention. But otherwise, you can just close your eyes, take a little nap, drift off to sleep, just let your mind relax a bit. You will catch a new ASMR math trigger word or two along the way. Who knows? So, let's get started, and don't forget to comment hi if you want to reach out. I always really appreciate it. So, yeah. Okay, let's go. So, first of all, we have a matrix A, and in this case, it's a 3x4 matrix, 3 rows, 4 columns. The first row is 1, 1, 3, 1. Then we have 2, negative 1, 3, 1. And then we have 1, 4, 6, 2. Okay. So in general, when you first learn about matrices, whether in linear algebra or just as a random miscellaneous topic, we often talk about them in the context of being a collection of terms, numbers, elements, and they are organized in this particular way where you can kind of index them by row and column. So you start with A11 and then going across A12, A13, A14, etc. And then going down you have A21, A31, A41, etc. So you can index each of these terms, and you learn about some basic matrix operations like addition, multiplication, inverses, and it's all interesting. But if you don't have any context for it or other ways of looking at them, it's nothing more than just doing a bunch of basic math and following certain patterns and putting them all in one place, which is fun, don't get me wrong, but I think where things get interesting in linear algebra is when we think about matrices in terms of vectors. And now we're talking about this idea of a null space, which is when we talk about the set of all vectors now. So it's this vector space, the set of all vectors, such that when I take this matrix and I multiply by a vector, it equals the 0 vector, and the set of all vectors x that satisfy this equation is inside the null space. And then we want to be able to describe what this actual set of vectors is, or what it looks like. And so now we just want to break this up, right? Break this down into concepts we already might know, but we're going to look at things from this perspective now. So if we have A times X, we might remember matrix multiplication. If not, I have other videos and don't worry too much about it. But basically the pattern is that we take the rows of the first matrix, so A in this case, and we take each row and we dot it with the column vector. In this case, X has just one column, but we would do one at a time and do every single pair if we had bigger matrices here. And now with the idea of vectors, we basically take rows of A and dot it with this column. And by dotting, I just mean we take corresponding terms and multiply together. So for the first row of A, I have 1, 1, 3, 1. And for the column X, I have x1, x2, x3, x4. So it's a four-dimensional vector. And so I do 1 in x1, 1 in x2, 3 in x3, and 1 in x4. And when I pair them, I just multiply them together. And then I add those products together to get one single expression. So that would be 1 times x1 is x1, 1 times x2 is x2, 3x3 plus x4. And that has to equal 0. So that's one equation. Then I have another equation. I take the next row and pair it with each of those variables, those components of this x vector. And I get 2x1 minus x2 plus 3x3 plus x4. And that has to also equal 0. And then same thing for the third, 1x1 plus 4x2 plus 6x3 plus 2x4. And that also equals 0. So the zeros are what make this the null space. You can associate null with 0. And so we basically have 3 equations and 4 variables. The variables being the 4 parts of our x vector. So x1, x2, x3, and x4. And so now we have a system of linear equations. And because the right-hand side contains all zeros, and aka those are constants, we have a linear homogeneous system of equations. So technically these constants can be whatever we want them to be. We could have 1, 4, -7. And we can use this trick of Gaussian elimination, which I've talked about in another video. But here in particular, we're talking about the null space. So we want all zeros there. Okay. And so that's exactly what we're going to do. We're going to try to look for a general solution for the x vectors that satisfy this equation and see if there's a pattern. So we're going to make an augmented matrix, which just means we're going to take something and then add something to it. So we're going to take our original A matrix, 1, 1, 3, 1, 2, -1, 3, 1, and 1, 4, 6, 2. I'm going to put a line, so I'm augmenting it. And then I'm going to put the zeros, the constant terms, on the right side of that line. But now I have a 3 by 5 matrix with a line to show that that's just the constant part of our system of equations. Okay. So, like I've said, we've talked about row operations before, but we can always come back, review. We're always practicing here. But the general idea is remembering that this thing represents a system of equations. We're going to basically use rules that we would normally use in basic algebra, like elimination, scaling an equation, and representing the system in this matrix form. And we're going to mess around with it until we get a simplified matrix that's equivalent and that represents an equivalent system of equations. And we want to reduce this thing as much as we can. So that's going to be called our reduced row echelon form. And we're just going to mess around with these matrices, manipulate them. That's what all these steps are in between to get to this reduced row echelon form. And all that means, before we get into the specific rules and stuff, is that this equivalent system of equations is as simplified as it can be. So, for example, if we were working with a system of linear equations from algebra, and we ended up with something like 2x equals 6, and x plus y equals 4. So, with 2x equals 6, that's not as simplified as it can be. We want the coefficient to be 1, right? So we would want x equals 3. because we have some overlapping x's there in the second equation, we can do substitution and actually get a value for y. So that's the idea. We want the coefficients of leading terms to be 1, and then there are just some other rules for the matrix that we want to end up with in reduced row echelon form, okay? But the big picture there is we're essentially using shortcuts and row operations to solve this system of equations to be as simplified as possible. That way we can get a general solution. And what that means is we just want a relationship between x1, x2, x3, and x4 as simplified as possible without much overlap or anything. There might be some free variables that we can choose whatever we want. And then, for instance, x4 might be open, so we can just let that be whatever value. But for instance, x1 might have to equal 3x in our general, or 3x4 in our general solution. So whatever we choose for x4, x1 has to be 3 times that number. So there might be some relationships and patterns there, and that's what we're after here, okay? So that's the general idea here. We start with our augmented matrix, and now let's actually talk about the rules and what we need to actually get to and what we're allowed to use. So our basic row operations, which is what I'm doing on this sheet, includes being able to swap any two rows. And if you kind of keep reminding yourself that this is just all about basic algebra, when you swap rows, you're basically swapping equations, and you can use them freely. So you can swap or interchange rows, and you have to do the entire row. You can scale a row by a constant, as long as it's non-zero, because 0 wouldn't give you any information. 0 times anything is 0. 0 plus 0 is 0, so you just get 0 equals 0, which is not helpful at all. So you can scale any row by a non-zero number, but you have to multiply every single element of the row by that constant. And then you can add or subtract any two rows, so one row from another. And adding and subtracting are the same, because for subtraction you're basically just scaling a row by -1 and then adding. So that's why I say add / subtract. But those are the 3 row operations that are allowed. And in my first sheet, which we'll go back to, I kind of combine them. So I might do like row 2 being replaced with row 2 minus 2 row 1. That's a linear combination. So that's a combination of scaling an entire row and then adding it to another row, which is totally fine too. You can break that into 2 steps if you want to, but you're allowed to just kind of put them together as linear combinations, okay? So that's the first thing. Just remember those 3 allowable steps, which stem from basic algebra. And then our goal for the reduced row echelon form is first we get into row echelon form, which just means that if we have a row with all zeros, which we sometimes do, sometimes don't, but if we have one with all zeros, it goes to the bottom, and then that means that the rows that are not all zero have at least one term that is non-zero, and that first non-zero term is the leading term or leading entry. And we want to have this pattern where we start from the top left, so the leading term is going to be on the top left, and as long as the leading term of the row below it is to the right, then we're okay. So we want the leading terms to kind of go from top left down to the top to bottom right, if that makes sense. So you can write that however it makes the most sense to you. You can start from the bottom right and kind of move up. So you could say the leading term at the bottom, besides the 0 ones, are always to the right of the leading term of the row above it. Or you can start at the top left and say that the leading term from a row is to the left of the leading term of the row of a row is to the left of the leading term of the row below it, if that makes sense. But you just kind of want to go at this diagonal, basically. So as long as you have all zeros on the bottom and you have this kind of staircase downward direction diagonal going on, Then you have row echelon form. And to make that reduced row echelon form, all that means is that those leading non-zero terms have to be 1. So you go ahead and scale it. So that's the equivalent of the 2x equals 6 being simplified to x equals 3. So you need those leading terms to be 1. And also for the columns that contain that leading 1 or a leading 1, you want all the other entries to be 0. So you'll get a feel for it as you can see here when we go back to our exercise. The idea of that is just the non-repeating variables, non-overlapping variables. You just want it to be as clean as possible so that we have it as simplified as possible. So you want 1s for all the leading non-zero terms, and you want the columns that have said leading 1s to be 0 everywhere else, and then you have reduced row echelon form. Okay, so now let's go back to our augmented matrix, and here I have all the different calculations here, but the idea is I start at the very top row. I see that there's a 1, so that's just a natural leading 1, which fits well with our reduced row echelon form, so I'll just leave it be. Then I notice that I have a 2 and a 1 for row 2 and row 3 as leading terms, and I want those to be 0 so that I can start this diagonal thing, and also so that I have zeros below this leading 1. So using those as the beginnings of an algorithm here for like what to actually do to simplify this. For row 2, I see a 2 and I already have a 1 above it. So I just replace row 2 with row 2 minus 2 row 1, because 2 times 1 is 2, and if I do 2 minus 2, I get 0. So I'm going to do row 2 minus 2 row 1 to get a 0 in that first spot. And then I just do the same for all the remaining terms and pairs of terms in the 2 rows. So the R2 minus 2 R1 comes from the fact that I have a 2 and a 1 in row 2 and row 1. The rest follows. So I do negative 1 minus 2 times 1, 3 minus 2 times 3, 1 minus 2 times 1, and 0 minus 2 times 0. That's how I get 0, negative 3, negative 3, negative 1, 0. Okay, so you just use those first terms to get your formula, and then remember that your row operations has to happen throughout the entire row, so you just do that calculation for the other pairs. Also note that I am doing a linear combination here, like I said before, and I'm trying to write out the actual operation that I did for the rows of the matrix above it. So in case you have to come back and check your work, it's good to know what row operations you did, which is why I do row 2 becomes row 2 minus 2 row 1. Do the same thing for row 3, and I'm comparing row 3 with row 1 because I just want to get rid of that one again, and I see I have a 1 leading 1 in row 3 and a 1 in row 1. So if I just subtract them, I get 0. 1 minus 1 is 0. So I do the same for all the other elements in row 3 and then minus row 1. So 1 minus 1 is 0, 4 minus 1 is 3, 6 minus 3 is 3, 2 minus 1 is 1, and 0 minus 0 is 0. So that's the R3 to R3 minus R1. And I'm doing this all in one because R2 and R3 are untouched. Like, we're just comparing them individually to R1. But if there is any overlap, you don't want to do that step in one go. You definitely want to stop and write the equivalent matrix first, and then you can use this new R2 in your R3 equation if you need to for the next step. Okay, I'm doing this all in one because we're just doing them relative to R1, and it's basically the same step. And also a little side note here is we just so happen to get 0, 0, 0 on the right, but we're still doing the same row operation. So like 0 minus 2 times 0 just happens to be 0. But make sure you're not forgetting this augmented side. Okay, you still have to do all those numbers. So if you had like 147, you still have to follow the expression and do it with those numbers too, just so so happens that with 0 here, they stay 0, so that's fine. For the next step, now we have zeros below this leading 1, but now we want the second row, the leading term, to be 1 as well for reduced row echelon. So we scale this -3 down to 1 by dividing by -3 or just multiplying by -1/3. So we do row 2 becomes -1/3 row 2. So I divide every element of row 2. So we're looking at the matrix above it and dividing it by -3. So that would be 0 divided by -3 is 0. -3 divided by -3 is 1, then 1, and then -1 divided by -3 or -1/3 times -1 is a positive 1/3, and 0 times -1/3 is 0. And then I also notice that from the augmented matrix above that row 2 plus row 3 is 0. They're actually the same but scaled by -1. So if I just do row 2 plus row 3, I get 0, 0, 0, 0, 0. Just so happens to be that way for this example. 0 plus 0 is 0, -3 plus 3 is 0, -3 plus 3 is 0, -1 plus 1 is 0, 0 plus 0 is 0. So that's fine. We leave the row with all zeros at the bottom, so that's good. And now we have this row echelon form, right? All zeros on the bottom. We have the leading terms in this diagonal from top left to bottom right. We just have a 1 and a 1 here. But we want this to be reduced, so we do have the 1s, but we need the columns with those leading 1s. So the first column is good to have zeros everywhere else. So we have 1, 0, 0 for the first column. But in this last step, or the second to last step, we have a 1 above this leading 1 in the second row. So we just subtract. It's okay. That's the idea of working with the 1s and then the zeros, because once we have leading zeros first in row 2 and row 3, whatever you do to that keeps your number, because anything times 0 is 0, and then anything plus 0 is itself. So you're not really going in circles. This is why we go from top down like this. So now if we just take row 1 minus row 2, the 1 minus 0 stays as 1, but 1 minus 1 is 0. 3 minus 1 is 2. 1 minus 1/3 is 2/3, and 0 minus 0 is 0. So that first row becomes 1, 0, 2, 2/3, 0. And now we have reduced row echelon form. Okay, so this is why I don't want to do all of the calculations in real time right now, because this is just all basic calculations. Of course, if we want to go back to basic operations, work with negatives, multiplication, all of that, no stress, no worries. I'm just assuming we're okay with that if we're working with this stuff. So that's the idea. And yeah, so we're gonna go from here. This is our reduced row echelon form for this augmented matrix. So now it's time to actually interpret this. Okay, so what I'm gonna do is, now that this augmented matrix is as simplified as possible, I'm going to translate this back into a system of linear equations. All I do is do the same dot product thing, where I take all the coefficients and multiply by x1, x2, x3, x4, and get the equations. Now, though, my system is more simplified, because with this third row being all zeros, that just tells me that one of the equations is equivalent to the other two combined in some way. It's just extra redundant information. So now I actually technically have 4 variables and 2 equations. So if I multiply this out, I get x1 plus 2x3 plus 2/3 x4 equals 0. And x2 plus x3 plus 1/3 x4 equals 0. And the reason why we don't have an x2 in the first one is because of the 0. So 0 times x2 goes away. And same thing for the x1 missing in the second equation. We have 0 times x1, so that'll just go away also. So now I have 2 equations, and that's fine. And we technically have 4 variables in all. Again, we're looking for our general solution, so x1, x2, x3, x4, if there's just some relationship between those. So I wrote those out because now I can notice that I can write x1 in terms of x3 and x4 just by taking that first equation and using regular algebra, moving the 2x3 and the 2/3 x4 to the other side. So x1 equals negative 2x3 minus 2/3 x4. And then x2 can also be written in terms of x3 and x4. So x2 equals negative x3 minus 1/3 x4. And then from this, x3 and x4 can be whatever we want. So our general solution for the four components is that x3 and x4 are whatever. They're independent variables, but whatever I decide for them to be, x1 has to be negative 2x3 minus 2/3 x4, and x2 has to be negative x3 minus 1/3 x4, and then x3 and x4. So if I have this particular pattern, then this vector would be in the null space of this vector A, this particular vector that we have. Isn't that cool? So as long as we have this particular pattern, it belongs in the null space. Cool. So from here, if you understand bases and linear combinations and stuff, some people can just look at this general solution and tell me what the null space is. It spans these two vectors if you line up x3 and x4, but I kind of want to go into this. It's a little bit tedious the first time you write it out, but I think it makes it the most clear. So the idea of actually defining this null space, we want to have some idea of what this space looks like, this vector space looks like. And what we do is, if we can say any general vector here, a general solution is a linear combination of, and if you can find two vectors that form a basis, in this case two, but in general any list of vectors that form a basis, then you can say that the span of these bases is my vector space. So let me think. So if we have, for instance, our three-dimensional space, any point x, y, z is a linear combination, meaning I can scale one vector and or each of the vectors and add them. So linear combinations are all about scaling by a constant and adding / subtracting. So if I have 1, 0, 0 and 0, 1, 0 and 0, 0, 1, any three-dimensional vector x, y, and z is going to be a linear combination of those three. So for instance, if I do 3 times 1, 0, 0, that's going to be 3, 0, 0. If I want to do, like, let's say 3, 4, 5, right? So it'll be 3 times 1, 0, 0 plus 4 times 0, 1, 0 plus 5 times 0, 0, 1. That will give me 3, 4, 5. So it's a linear combination of those three. So those three, which correspond to 1, 0, 0, 0, 1, 0, and 0, 0, 1, form a basis for our three-dimensional space here. So it's kind of like that. So in this particular case, for my null space, if I rewrite this general solution in terms of x1, x2, x3, and x4, then I can put the zeros back in, and this makes it the most obvious that we're looking at linear combinations of particular vectors. So this makes it, that like structure, more clear. So that's what I'm doing here. I'm taking our general solution, but I'm putting 0x1 plus 0x2, and then keeping the variables in our solutions the same, so negative 2x3 minus 2/3 x4. Then we have 0x1 plus 0x2 minus x3 minus 1/3 x4, and then 0x1 plus 0x2 plus x3 still plus 0x4, etc. 0x1 plus 0x2 plus 0x3. Then I got it messed up, but plus x4. And the reason why I want to do that is because now I can break this up into column vectors, and I factor out this x1. So x1 times 0, 0, 0, 0 plus x2 times 0, 0, 0, 0 plus, and now those two just go away, but if I factor out x3, I get negative 2, negative 1, 1, 0, and then plus x4 times negative 2 thirds, negative 1 third, 0, and 1. So this is like the most direct visual way of seeing a linear combination. You have a constant x3 and constant x4 scaling the column vectors, and this still applies. Remember how to actually add vectors, that all still matters here. So that's what we're actually doing. We're making this very clear, very clearly a linear combination. So that means that the two column vectors, the zeros go away. The two column vectors form the basis, because whatever solution we get, we are going to have a linear combination of these two. So negative 2, negative 1, 1, 0, and negative 2 thirds, negative 1 third, 0, 1 form a basis for our null space. So therefore our null space is equal to the span of these two. And because there are two vectors that form the basis, the nullity is 2. So the nullity is just how many vectors span this thing. So that's the general idea. So of course you don't have to write 0, 0, 0 every single time, and our general solution is going to look different depending on our original matrix A. This just happens to be our general solution for right now. But sometimes you'll have two independent variables, sometimes you'll have more, sometimes you'll just have one. So as you practice that, you can keep in mind that as you have your general solution, you kind of want to write those vertical column vectors back, and sometimes you can just write that, put the zeros in where you want directly, but otherwise you can just go through this exercise and expand it back out. But it'll be the span of these two vectors in this case, and so therefore the nullity is 2. So I hope that this was interesting if you were curious about it. Otherwise, I hope that you found this to be relaxing, boring, whatever, just something to zone out to. If you are asleep right now, I'm wishing you sweet, sweet mathy dreams. If you're continuing on with the rest of your day, I hope it's a good one. And I'll just continue jumping around a bit. It's fun getting back into this, so I will see you around for more math and ASMR and math. I'll keep you posted